All right, line A6, learning task 9, values for rectified power supplies. We have gone over the theory for three-phase rectifiers. We've taken a look at the half-wave rectifier. We've taken a look at the full-wave rectifier. Now what we're going to do is we're going to go and use transformer theory along with rectifier theory to go and create values that we would be able to go and utilize. Now some of you are saying, why are we looking at such massive values of DC? To be honest, there is a huge use of DC in heavy industry, particularly in chemical processing. There are so many electrochemical processes where we are going to go and use electrons to go and carry stuff, electroplating or taking stuff apart. You take a large saltwater brine, you heat it up, you hit it with a couple thousand volts of DC running through it, you're going to be able to go and separate that thing into hydrochloric acid and caustic soda, both of which are great industrial chemicals that have their uses for different stuff. You wouldn't want to touch either, but these are things that allow us to create and do a lot of the industrial systems that we need. So we will use massive values of DC, and in a lot of cases we're going to go and have three-phase systems, because where we use these big values of DC is going to be on other places where we've also got a lot of pumps and motors and things like that. So we're going to come from DC, or from three-phase, we're going to go and change that into DC, and then we carry it around our plant in what we would refer to as a DC bus system, where we're then able to go and take it off and use it to run the actual DC loads that we see ourselves using there. So let's go through our examples over here. The very first example that they give us is going to be a three-phase half-wave rectifier circuit. It's to be supplied from a transformer bank, as shown in Figure 1. Primary supply to the transformer bank is 2400 volts, three-phase, 60 hertz. Each transformer has got a turns ratio of 10:1. And then they want to know what's going to be the DC voltage that I'm going to measure across the load resistors. So we want to go and start by finding this value of voltage. Then they're going to say, we know what our resistance is, 6 ohms, low value of ohms, which means we're going to go and have a high value of current. This is going to be the same inside of all of our chemical systems, etc. Ripple frequency, PIV rating for each diode to make sure that this thing's not going to go and blow up. So the peak inverse rating for each of these. And then the average DC current conducted by each diode. I'm interested in the average, by the way, as well as the actual current that's going to be conducted by each, because I'm going to need to know the peak value of current as well as my average value of current. If I have take anything, I can overload anything for small amounts. So we know this, that if I go and take this and I take a massive slug of current through this thing, boom, like that, it's going to go and heat it up. But then if I give it a bit of time to cool down, then it's not going to be as hot. And then I can give it another boom, big slug of current that's going to go through it. This is what the average is talking about, because we're going from this one to this one to this one, this one to this one to this one, etc. around. Okay, let's start with a redraw off of this thing, because right now it is showing us this as a delta to Y type of setup. And if I take a look at my connections are pretty good over here. I see that I'm creating a neutral. I'm feeding back to a neutral. I have gone and grounded my neutral on my system that I'm going to go and have over here. But it's still a little bit difficult to go and see what it is. So I'm going to go and draw this as being two systems like this. Pause the video, draw it out yourself if you wish. Just know that my H1 I'm feeding power in is going to go and flux over to my X1 winding over there. My H2 is going to go and flux over to my X2, and then my black phase is going to go and flex over to my black phase over here, right? So we're just going to go and transfer everything through magnetic fluxes from one to the other. We're going to go and use our transformer ratios to go and step through, because until we establish the value of voltage on the secondary, we're going to have no idea what we would have for our average. So we're going to start with this 2400 and with this 10:1 ratio. If it is a 10:1 transformer ratio, this is not a line voltage ratio, this is an actual transformer ratio, 10:1 means that my high side is 10 times larger than my low side. So I'm going to take 2400, divide it by 10. I don't need a calculator for that. You don't need a calculator for that. Nobody needs a calculator for that. 2400 divided by 10, we just knock a zero off, and we end up at 240 volts. So this winding is going to be 240 volts going across from here to here. Okay? This is important that we recognize that this is 240 volts going across from my neutral to my line, which means that overall my line value for this is going to have to be higher, right? From here to here, because if this is 240 volts, then this is going to be 240, and this is going to be 240. We can draw it as being just off on the side here, 240, 240, 240. Our line-to-line value on a y has to be root 3 times larger. So we're going to go and take 240, and we are going to multiply it by root 3. 240, that's my phase value, times root 3. Okay? Gets me to 415.9. We commonly call this voltage 416. It's not a super common value of voltage, but it does happen occasionally out there. So this is now going to be a 416 line to line. Beautiful. Okay, I'm just going to go and erase all of these here now. Now that I have that, I'm going to go and analyze what do I have happening inside of here. Well, we have got a half-wave rectifier circuit, which means that at any given time, I'm only going to be transmitting voltage from a single coil. The other two coils are going to go and be blocking at any given time. So let's go and pick one of these coils to be our high coil. I'm just going to pick this one right now. We're going to say that this one here, my C phase, is going to be my highest given point at any time, which would mean that it would be passing and the other two would be blocking. So I could go and trace this through, if it's the most positive one. I could go and trace this through and say that I'm going to be delivering current down here. That dotted line is the neutral, just because the white line doesn't show up, and transferring through like that. This would be my value of voltage that's going to go through there. I would start with that one, then I'm going to go and move on to my next one. My next one, they're all going to go and take turns, but ultimately all of that current is always going to travel through this 6 ohm resistor in the same direction. Since we know that we are dealing only with the phase value of voltage, what we can do is we can go and use our form factor formula for this one. Our form factor for a half-wave rectifier is going to be 1.17, and I multiply that by my E phase. Well, my E phase in this case is going to be that 240 volts just across that phase. So I'm going to go and take 1.17 times 240, which is going to go and get me to a value of 281 volts. This is going to be my average value of DC voltage. So this becomes 281 volts DC. Make sure when you guys are writing these answers that you start subscripting volts DC, volts peaks, etc., because we're working with multiple different types of voltage inside of here. Well, if I've got 281 volts DC over top of there as my average value, what is my current going to be? Well, that's just going to be straight Ohm's law. I is equal to E over R. Ohm's law works the same for DC or for AC. So I'm going to go and take 281 as my value of E, volts over here, 281. And I'm going to go and have 6 ohms as my value of R. 281 divided by 6 is going to go and get me to a value of 46.8 amps. And it's really important to note that that 46.8 amps is going to go and flow through each one of these windings. I'm going to have 46.8 amps that is going to go and flow through here. And then it's going to be this one's turn to carry 46.8, and then this one's turn to carry 46.8, which means that each of my diodes is going to have to be rated for a peak current, I peak, of at least 46.8 amps that I'm going to go and have. So we're carrying 46.8 amps through here. What can I do with that 46.8 amps and that 281 volts? If I wanted, I could actually go and figure out my value of watts from this one as well. They don't ask for it, but you just have to go and multiply together 46.8 times 281, which would get you to your total value of watts that you would have off of that resistive load over there. Let's just do that just for fun. 281 times 46.8 brings us to 13 kilowatts that we are going to go and see over here. Well, that was fun. 13 kilowatts. Why do I like kilowatts? Good question. Because watts never lie. Ultimately, what am I taking out of this system? 13 kilowatts. How is that 13 kilowatts getting through here? Well, you're telling me it's coming in through this rectifier circuit. Perfect. It is coming through the rectifier circuit. Well, the rectifier circuit is fed by this transformer winding here, which is being fed by this transformer winding over here. VA in is equal to VA out. So what I can really do with this 13 kilowatts is I could go and figure out my I line primary, which is really exciting because if I had to go and convert this DC into an AC, take it through here, convert that AC into another AC onto here, this would be a major pain for me to go and do so. It's much easier for me to go and take this 13 kilowatts and drop it right over here and say 13,000, VA in is equal to my VA out. If I'm delivering 13,000 minus the small amount of losses, I must have that amount coming in, and so I could figure out my primary line current off of here. We do need this inside of industry. Okay, last couple of things that they ask for is they ask for ripple frequency. Well, if it's a 60 hertz system and it's half wave rectified, my ripple frequency is going to be 3 times whatever my fundamental frequency was going to go and be. So 60 times 3 gets me to 180 hertz that I'm going to go and have for this one. We are also going to go and have to figure out what is going to be my maximum that each diode is going to have to go and block. And once again, we can go and highlight and say that anytime one of these is passing, let's say that this one is passing, then this one would have to be blocking. And if I take a look at the path that that one is blocking, it is blocking voltage from here, from getting across to voltage, because this one is passing, through to here. So it is seeing the same thing as a line to line value of voltage across there. So we need to go and block the line to line value of voltage, but not just the line to line, but the peak of the line to line value of voltage. Over here we had 416 volts, so we're going to go and take that 416 volts, which is the RMS value, divide it by 0.707, because that is now going to take us to a peak, and when we do so, we come out to a value of 588 volts. So we would need to be blocking at least 600 volts on each of these for my PIV. Last thing to talk about is the average DC conducted by each diode. Average DC is going to be a value that's going to be 1/3 because each one is going to go and carry all the current for part of it, 46 amps. And then the next, when this one's carrying, it carries 0. And then when this one's carrying, it carries 0. So 46 plus 0 divided by 3 times, 3 time constants, is going to bring us down to a value of 15.6. For my ratings on my diode, this stuff is important because industrial diodes, we call them just industrial rectifiers, are going to go and be expensive, large units, and when they fail, they can fail catastrophically. Us putting AC into a DC section is going to go and change what's happening inside of it. Recombining chemical processes and stuff like that can be, highly explosive type of thing. So I'm going to go and have to figure this stuff out safely. I need to go and have a PIV of 600. We hit 588, but 600. I'm going to go and have an I peak of, it was 46.8. We're going to call that a 50 amp that I'm going to be looking for. And an I average of 16. We'll round up that 50. I would be going into my rectifier tables, and this would be what I would be looking for. My peak values of current, and then my average values of current. Okay, that is our calculation. Last thing that we're going to do was something that we said, look, what we need to do is we need to go with our kilowatts because our kilowatts aren't going to go and lie to us. We are going to go and figure out our line current on the primary, which is going to be really easy because VAN is equal to VA out, and I know that I line for a transformer, and it doesn't matter what it is, can be found by taking my VA divided by my E line times √3. I see it's a 2400 volt delta, therefore my line value of voltage has to be 2400 volts line. So I'm going to be able to take this 13,000 divided by 2400 times √3. 13,000 divided by brackets 2400 times √3 bracket gets me out to a value of 3 amps that I'm going to go and have on my primary. Doesn't seem like much, but most of our high voltage stuff is going to be operating at relatively, what we would consider relatively low values of current that we use to go and run, transform into lower values of voltage and much higher kilowatts. Okay, that was our first one. That was our half-wave rectifier. That one was nice and easy. Let's go and take a look at our next one, which is going to be a 3-phase bridge rectifier circuit that's full wave. So it's going to be a full wave one here. If I take a look, I see 6 diodes. 6 diodes or 6 SCRs or 6 rectifiers of any sort is usually going to go and mean that I am looking at a full wave rectifier. I can double check and just see if my values of voltage are going to be fed back in from either side. And I do see that I've got that, that I can feed to my load from either one of these. If this one over here was going to go and be negative into my load. I could have another line that is going to be currently positive, and I would be able to get a line-to-line value of voltage. We can pick any two. We just have to look and see if there's going to be a complete path for this to go and happen through. To supplied from transformer bank as shown in figure 2, the primary line voltage is 4160 volts, 3-phase 60 hertz. Each transformer has a turns ratio of 10:1. And it does have a Y delta. This is very common on one-line diagrams that we're going to go and see a Y delta or delta Y or Y over Y. And it just tells us what that ratio is going to go and be, or which one we're using on the top, which one we're using on the bottom, so we can figure out what we've got for values of line and what we have got for values of phase that we are going to go and have. I'm going to go and do a redraw because I don't like this drawing for doing the explanations quite as much. I'm going to go and show my redraw over here. My redraw says the exact same things, 4160, that I'm going to go and have line to line. It's connected in a Y, and so we see that all on this side over here. We've got the same transformer ratios, 10:1. And if I take a look at what I have over here, I can go and follow this connection. It's a delta connection, but I can go into one, out to the next, into one, out to the next, and back over. We can form that complete loop the way that we did when we were looking at transformers. So I've got this delta system where I'm going to go from one to one to one onto the other one. Perfect. Well, what are we going to do? We are going to go and figure out what we have got line to line on our secondary side. The way that we're going to have to do that, though, first is we have to go and figure out our E phase primary, right? Because we see that my transformer, each transformer is just fluxing across. This one over here is going to go and flux across to this one over here, and it's going to give a 10:1 value of voltage of whatever this winding is to this winding over here, okay? So let's go and figure out what each of those phase values are on my primary. Well, if my primary is 4160, that is going to be a line-to-line value that's given to us in the problem. So we're going to go and take that 4160, E line, divided by root 3. 4160 divided by root 3 is going to go and get me down to a phase value of 2400. Well, once again, transformer turns ratio of 10:1. So if I've got 2400 divided by a 10:1 ratio, it's going to bring us down to 240 volts that we are going to go and have on each of our secondary coils. Each of our secondary coils is 240 volts. What is my secondary system? My secondary system is going to be delta, which means my phase value of voltage is going to be the same as my line value of voltage. So if I've got 240 volts phase, I have got 240 volts line. That is going to go and happen as well. Let's take that line value of voltage now that we are outputting, and we are going to go and do all of our calculations off of it. Remember that the half wave works off of phase values. The full wave is going to go and work off of line values over here. First thing we're going to do is we're going to go and take our form factor. Form factor is something, once again, that is just a bunch of equations combined together into a magic soup that we're going to be able to apply in the proper place. In this case, the form factor is going to be 1.35, and we multiply it by our line value of voltage to get our DC average. We said that 240 volts was my phase, but because it was delta, 240 volts was also my line. So we're going to go and take 240 times 1.35. When we do that, 1.35 times 240, we come out to a value of 324. Beautiful. 324 volts that we are going to go and have. So this is going to be what I'm going to place across my load resistor over here. 324, let's put that down here. 324 volts. Lovely. Okay. With that 324 that is being placed across there, we can now figure out my currents that I'm going to go and have based on my value of resistance that's given over here. I is equal to E over R. Ohm's law works in AC or DC, so we're going to use it in DC here, 324 divided by 4. I is equal to E over R, which is going to go and give us a value of 81 amps. So I'm going to go and have 81 amps that is going to go and pass through here. That 81 amps is going to allow me to go and do something magical once again. What is this beautiful thing we like to do? We like to combine these to get to watts, and instead of going back through calculations to calculations to calculations to calculations, which would screw us up. We'd like to go and take this total amount of watts, and we'd like to run it right out to the outside, so we can do VAN is going to be equal to my VA out. Let's do that really quick. 81 times 324. It's not inside of your book, so we'll just quickly do that. 324 times 81 gets me out to a value of 26.2 kilowatts. So my total, 26.2 kilowatts, which means that over here, 26.2 kilowatts as well. Let's just finish up here on this high side, and then we'll go back to the other calculations. If this 26.2 kilowatts over here, I know that I can find my I line. It's equal to my VA divided by my E line times root 3 over there. So I'm going to do that. I'm going to go and take this 26.2 kilowatts, put that in as my VA, divided by my E line. My line voltage on my high side was 4160 times root 3. Okay, so we'll just clear that. Oh, I guess I could have left that in there. 26,200, we rounded it. Divided by my E line, 4160 times root 3, which gets me to a value of 3.6 amps that we're going to go and have. Once again, just critical for figuring out what I'm going to need to size this wire for, 3.6 amps. Lovely. Okay, that takes care of my power through this thing. Watts never lie, guys. You just have to trust the watts. Figure out the watts over here, the load. Then don't bother dumping them through here and dumping them through here, because that's going to be a major pain in the butt. Take them directly over here. We do know that this thing is delivering a total of 26.2 kilowatts, which means that we could also use that 26.2 kilowatts here to go and figure out my line values of current and stuff like that inside of each of these two. We're not looking for that right now. We usually are just looking for what do we have incoming and what do we have outgoing off of these. Last values that they're looking for off of these was going to be my ripple frequency. My ripple frequency, because we're full wave, is going to be 6 times my fundamental. So 60 hertz times 6 is going to be 360 hertz. It's going to be jumping around back and forth pretty rapidly. And then my PIV ratings for these, my peak inverse ratings, have to be, once again, at least equal to my line value. So if I take a look at this over here, any one of these diodes, when they're blocking, is going to be blocking against a full line-to-line value of voltage. So I'm going to go and take this 240 volts, which is my line value, divided by 0.707 to take it to a peak. When I take it to a peak, it is then going to go and tell me that my peak value voltage is going to be 340 volts that each of these needs to go and block against. You can use a 1.414 or you can use the 0.707. Last thing that they talk about is going to be the average value of current carried about by each of these. Anytime that I'm running through one of my paths on here, let's just go and highlight any value of path over here. We're going to say that this is going to be my high and my low. So actually, why don't I just put this over here? We'll say this is the most positive point. This is the most negative point. This one's in between. So we're just going to be blocking off of both of those ones over there. And if I were to go and take a look at which diodes are going to be forward biased, I would see that my positive would be passed by this one over here. And if I were to take a look at my negative, I would say that my negative, we'll pick a different color highlighter, would be passed by this one over here. It's going to pass that negative one down to there. So my negative is going to be on this side of my load. My positive is going to be on this side of my load over here. And I'm going to go and pass that through there. Well, if I take a look at, let's pick any one of these diodes. Let's take a look at this one right over here. If I take a look at that diode, I see that it's connected basically right over here. That point, call that thing my A line. And it's also connected, we'll follow this blue all the way back through here to my B line. It's connected all the way across from A to B, which is going to be a full value of line-to-line voltage. And because it peaks, because it's AC, we need to make sure we hit that peak. The average value of current that's traveling through here, we see that my current, all 81 amps, which we calculated before, is traveling through this diode as well as it's traveling through this diode. It's a series circuit that is basically diode, load, another diode is what we're always going to be going through. So each pair of diodes is going to go and spend a little bit of time conducting, then the next pair of diodes is going to spend a bit of time conducting, and the next pair of diodes is going to spend a little bit of time conducting. So each one of them is once again going to carry a third as being their average value. For my diode ratings, this brings us now to the fact that my PIV needs to be 340 volts. We'd have to go higher, obviously, just in case there's transients on the system. My I max or I peak, is going to have to be 81 amps that I could carry through each of those diodes. And my average is going to be a third of 81. So we'll just go and take 81 divided by 3, which is going to be 17 amps. My average is going to be 17 amps. I would be looking for a data sheet out of my industrial rectifiers that would go and give me these values over here. Okay. That's it for the rectifiers. We're done with them. We're going to move on to our next subject. Once again, last thing, VAN is equal to VAO. So critical because it allows us to do any other calculations. In this case, we said it was 26.2 kilowatts that we had. It's all resistive, all over here, which would mean that I'm going to go and have 26.2 kVA because my kilowatts and my kVA are going to be the same over here, and I can use that kVA to calculate line values of current, and 26.2 kVA over here. Just makes your life a heck of a lot easier.